would like to introduce myself. So I am Shemaine Ang, an incoming freshman at Imperial College London studying electronic and information engineering, and I am a woman who code Python volunteer. With me, I have another speaker, Shivanji, an SD2 at Griffith, India, also a woman who code Python track volunteer. With that, let's get started on today's agenda. So firstly, we will talk about what are trees, terminology of trees, examples of trees, before moving on to what is a binary tree, and then talking about what is a binary search tree. And then we will go through some binary search tree operations, such as counting nodes, searching, insertion, and traversal, before moving on to our live coding session. And then we will show you some resources and preparation that you can use. With that, let's get started on today's session. So firstly, what are trees? So a tree is a non-linear data structure which organizes data in a hierarchical structure. Trees have two main characteristics. Each item can have multiple children, and all items except a privileged item called the root have exactly one parent. So you might be quite confused with all these terminologies right now, but don't worry, as we'll be going through it right now. So firstly, a node, which is an item stored in a tree, and we have a root, which is the topmost node in a tree. So in this tree below, A is the root node. In any tree, the first node is called a root node. Next, an edge. So an edge is the connecting link between any two nodes. So in the diagram below, you can see that the edge is the connecting link between A and C, A and B, B and D, and so on and so forth. So this is what an edge is. Next is a parent. So the parent node is a node which is a predecessor of any node. So in the following diagram, you have A, B, C, E, and G as parent nodes. In any tree, the node which has child or children is called a parent node. And a node which is a predecessor of any other node is called a parent node. Next, we move on to a child. So a child is the node which has a link from its parent node. So here, B and C are children of A, G and H are children of C, and K is a child of G. So a descendant of any node is called a child node. Next, we look at what are siblings. So siblings are nodes which belong to the same parent. So B and C are siblings, D, E, and F are siblings, G and H are siblings, and I and J are siblings. So in any tree, the nodes which have the same parent are called siblings. The children of a parent are called siblings. Moving on to leaf. So a leaf is the node which does not have a child. So in this tree below, D, I, J, F, K, and H are called leaf nodes because they do not have a child node. So in any tree, the node which does not have children is called leaf, and a node without successors is called a leaf node. Next, we move on to what is a level. So it means each step from top to bottom, starting from level 0. So in this tree, we have a total of level 0, level 1, level 2, level 3. So we always start with level 0, and then we increase as we go down the tree. Next, a subtree. So a subtree is where every child node will form a subtree on its parent node. So we look at the root node A, and then we look at the children B and C. So B forms a left subtree, which is this pink circle over here, whereas its child E forms another subtree at the bottom, which consists of E, I, J. Whereas on the right-hand side, C forms a subtree with G, H, and K. So moving on to what is a binary tree. In a binary tree, each node has at most 2 children, the left child and the right child. Components of a binary tree, you have a data element in the center, a left pointer, and a right pointer. So now let's look at the diagram here. So we look at the root node A. It has the data element of A, and then the left pointer is pointing towards the node which has B, and the right pointer is pointing towards the node which has C. So now let's look into some examples of binary trees. So we have full binary tree, complete binary tree, and perfect binary tree. But what do all of these binary trees mean? So a full binary tree is a binary tree that has either 0 children or 2 children. So this is how a full binary tree looks like. So your parent node 2 has 2 children, 7 has 2 children, 6 has 2 children. So now we move on to a complete binary tree. So all the tree levels are filled entirely with nodes, except the lowest level of the tree. In the lowest level of the binary tree, every node should possibly reside on the left side. So this is how a complete binary tree should look like. As you can see, all the tree levels are filled entirely, except the very last level here, where all of the nodes are at the left side of the binary tree. So this is an example of a complete binary tree. Next, we move on to a perfect binary tree, where all the internal nodes have strictly 2 children, and every external or leaf node is at the same level or same depth within a tree. So this is how a perfect binary tree should look like. All of them have strictly 2 children, and those without children are all at the same level, which is where 1, 3, 5, 7, 9, 11, 13, and 15 are at. So here's a quick comparison between full binary tree, complete binary tree, and perfect binary tree. So now let's compare between binary trees and graphs, since they all seem quite similar. So in a graph, we do not have a root node, whereas in binary trees, you have exactly 1 root node, as you can see in the diagram on the right-hand side. In the tree, your root node is A, but in a graph, you don't have a root node. In a graph, you can have loops, but in binary trees, no loops are permitted. So in the diagram on the right-hand side, your graph, you can see that there's a loop going D, E, F, G, H, and it goes back to D. Whereas in a binary tree, such loops will not happen. And the last difference is that in a graph, each node can have many number of edges, but in a binary tree, every node can have at most 2 child nodes. With that, let's move on to what is a binary search tree, or BST for short. So binary search trees are sorted binary trees. So this means that the value of all nodes on the left subtree is less than or equal to the value of its root node. The value of all nodes on the right subtree is greater than or equal to the value of its root node. The left and right subtrees are also binary sort trees respectively. So this is an example of how a binary search tree will look like. So 5 is smaller than 9, so it's placed on the left-hand side. 2 is smaller than 5, so it's placed on the left-hand side. And 1 is the smallest, so you can find it all the way at the left. Whereas all the way on the right, you have the biggest number. Some pros and cons of using a binary search tree. Pros include quick searching, quick insertion, and quick deletion. However, some cons of the binary search tree is that implementation might be quite difficult. Now we move on to some binary search tree operations. So before you want to create your binary search tree, you have to first create a node, which is your root node. So your root node will have a data element, a left pointer, and a right pointer. So this is how the code will look like. So you create a class called tree node, and then you put your left pointer and right pointer as none. And then your data element as what you want to put in your data. We will explain on this code in detail later during our live coding session. So don't worry if you don't understand what the code is saying now. So next, we can count the number of nodes. So you want to determine the number of nodes in a tree by counting the number of nodes in the left subtree and then the right subtree. So this can be done using recursion. So if the tree is none, that means that the tree is empty. It will return 0 straight away. If not, it will count the number of nodes on the left subtree and then the right subtree, and it adds 1 because this includes the root node. The next operation is searching. As the binary search tree is sorted, if the item is less than the current data, it will continue searching in the left subtree. So in this code below, if tree is none, it will return false as it's an empty tree and you can't find the item that you're looking for. If it's not none, if the item is less than the current data you're on, it will search in the left subtree with that item that you're searching for. However, if the item is currently bigger than your current data, it will move on to the right subtree. And the last 2 lines of the code shows that the item has been found, so it will return true. And the searching algorithm has a time complexity of OH, where H is the height of the BST or the level of the BST. So this is an example of searching for 27. So let's go back to the start. So 27 is bigger than 21, you go to the right. 27 is smaller, go to the left. Bigger than 25, go to the right. And then you can find 27 in the end. So next operation would be insertion, which is to ensure that the binary search tree is still sorted, item will be inserted at the root node if the tree is already empty. If not, the item will be inserted at a node in the current node's left subtree if the new item is less than the item in the current node. However, if the new item is greater than or equal to the item in the current node, the item will be inserted at a node in the current node's right subtree. And the time complexity is the same as that of the searching algorithm, which is OH. So you start with a root node, you insert 28, since it's bigger, you move it to the right, 14 is smaller, move it to the left. And this will keep going on and on for all the items you want to insert. So next, we go into traversal. So traversal is the process of visiting each node in a tree data structure exactly once. So we have different types of traversal. Firstly, we have pre-order traversal, in-order traversal, and lastly, post-order traversal. So let's move into pre-order traversal first. So what it does is it visits the root node and then traverses the left subtree and the right subtree in a similar way. So in the diagram below, it visits the root node D first before moving to the left subtree, and then it goes into B, and then it visits the left subtree of this, which is A, moving on to the right subtree C, and then since it finished visiting the left subtree of the root node D, it moves into the right subtree, which consists of F, E, G, and it repeats itself. It visits the root node F, traverses the left subtree E, traverses the right subtree G. So this is the order of the nodes visited. So it's root, left, right. With that, let's move on to in-order traversal, which traverses the left subtree first, visits the root node next, and then traverses the right subtree next. So in-order traversal is also the same as printing your nodes in order. So in the diagram below, you first traverse your left subtree. So you go all the way to the left node, which is A, and then you visit the right node, the root node of this tree, which is B, and then go into the right subtree C. And now since you finished traversing the left subtree, which consists of A, B, and C, you move back to the root node D. And now you traverse your right subtree, but you do it the same way. You go left, root, right. So you start with E, F, then G. So it's left, root, and then right. Now we move on to the last type of traversal, which is post-order traversal. So what you do is you traverse it. It traverses the left subtree, traverses the right subtree before visiting the root node. So the orders of nodes visited for this binary search tree. So it goes all the way to the left, which is A. It goes to the right subtree, which is C, before visiting the root node B. And now since it's finished traversing the left subtree, which consists of A, B, C, it goes into the right subtree and does left, right root. So E, G, F, before visiting the root node of the binary search tree, which is D. So D is your last node visited. So it always starts with left, right, and then it goes back to the root. Left, and then goes to 17, and then 16. So it's this left, right, and then the root. With that, we will now have a Q&A session. If any of you have any questions, feel free to put your questions in the Q&A chat. Does anyone have any questions for now? Okay, see.
I can read out the question for you.
Okay, sure.
If that would help you. Yeah, so the first question is, when should we be using different traversals and how should we know that?
Okay, so if you want to print out your notes in a sorted order, then you would use Inorder Traversal. If not, it's really up to you on what kind of traversal you want to use and in what kind of order you want your notes to be printed out, then you use that traversal accordingly. But most of the time we would use Inorder Traversal because we want to get the data in a sorted order. So that's like the most commonly used traversal. I hope that answers your question.
There's one more question in the chat.
Okay.
For big O, when calculating, does level 0 count as 1?
Hold on, let me think. Yeah, it does count as 1 because if the item you're searching for is in the root node, that would be considered as 1. So your level 0 count as 1. Yep.
Okay, great. Let's see, another question in the Q&A is, hi, can we consider HTML as binary tree?
Wait, I don't really understand that question.
Sorry if I'm mispronouncing your name, Nada or Nada. If you could perhaps clarify your question so we can answer it.
Do you guys want me to take a stab at it?
Yeah, if you would like.
Yeah. So Neda, I understand where you're coming from. Considering HTML is a markup language and you have some parent and child tags, right? I would not say you would consider it as a binary tree. It's more of an n-ary tree, right? Because you don't know, you don't have a limit to how many childs it can have, right? So it's not necessarily a binary tree, but it's more of an n-ary tree, meaning it can have n number of childs at any given point of time. Does that answer your question? Neda?
Yeah, I think
Yeah,
that was
answer.
answered.
Thank you so much, Shivanji.
You're welcome.
All right. No more questions for now, and we can definitely pause again after the live coding section for another round of Q&A, but for now we can switch over to the live coding session.
Yep, so now Shivanji will take over for the live coding session.
Yeah, thanks, Shami. Thanks. Could you guys give me a minute? I'll present my screen.
Sure.
Let me know when my screen is.
Yep, we can see it. It's yeah, it looks good.
Yeah. All right. So hey everyone. So the agenda for today is going to be how can you create a binary tree, right? And how do you traverse these binary trees? And the second part of the agenda is going to be about regarding BST. How do I create a binary search tree, and how do I insert elements into the binary search tree? And there are a couple of questions from LeetCode. There's a question from LeetCode as well. So yeah, let's just get started. So Sherman spoke about the the structure of the object you need for creating a binary tree, which is the node object, node class in this case, right? So it has three elements. One is the data or the value which you want to store, right? And the other is the pointer to the left subtree and the pointer to the right subtree. So does everyone, before I even get started with the coding part, has everyone just forked the Colab notebook? Is there any issues with that? Let me check that. Could I get a thumbs up if everyone's forked the notebook? Cool. Should I get started then? Okay. So I'm going ahead and starting since most of you guys were able to fork the notebook. So over here, we're going to define a class, right? And we're going to call this class node. And this has to have these elements, right? So as you know, when you are initializing a class, you have to define an init function, which is basically the constructor. And whenever you're dealing with classes, you have to have the self object, which points to the instance of the class which you will be initializing, right? And over here, I can give some default values as well. So I'm going to initialize my left pointer as none. Right? So data is one element, and the other element is left pointer, which is none. And then there's the right pointer, right? Now, will anyone want to guess how the next part would look like over here when it comes to the allocation? Because we'll be doing this a little often today. So does anyone want to try to give it a chance? How do you think you will assign the values over here? Nadia says self.data. Yeah. So what you essentially do is you have to copy this value which you're passing to the constructor to the instance. So like I said, self points to the current instance. So I'm going to copy the data like this, right? So similarly, I can just do it for the left pointer and the right pointer. So now we have defined, yeah. So now we have defined a class, right? Now we've defined the class. That's the first step. Now, how would I, view the data inside this class? It's an object, right? If I try to print it out, it's gonna look kind of weird. So let's just try how it's gonna look. So for example, let me just initialize L to be a node, right? And okay. And let me try printing this out. What do you guys think will happen? Anyone, any guesses? Okay, let me just do this and see what happens. So basically, what is this, right? It's showing you a memory location of where this object is being stored. But honestly, I didn't want to see this, right? I wanted to see what was inside this node, right? So what you could do essentially is you could kind of define a string function over here, which is like a function which you can use for printing this information, right? So what we can do is we could essentially say, let's call this a pretty string, right? Because this is kind of ugly. I don't understand what's happening here, right? So let's just define how we want it to look like. So this is the node. And what I'm going to do here is I'm going to format the data, right? And I'm going to show it, right? Let me just do one thing. I'll just use, I'll use the format string, right? So essentially, if I have to print the left subtree, what do I need to do? Anyone? Would you want to give it a try? It's very similar to whatever we were trying to do here, but why don't you guys try it? Okay. Right. So, yes, self dot left. But again, now self dot left inner tree is actually an object, right? So if I again try to print it, it's going to give me this amazing memory location, right? Which I don't want. So basically, I need to print the data inside that object, which is going to look like this, right? Now, one thing I would want to do here is, just for an example, I did this. But there are cases where this could be none as well, right? So what I'll do over here is, I'll just move this information a little outside over here, right? And I'll just format it outside. Okay. And over here, I'll just say, if you find that this is a null object, right? Just print. So if there is some information in the left pointer, only then print this, otherwise print a none object. Similarly, I could do the same for your data, or I could even call this root, or data, whichever makes sense to you. So let's just call this data because I want to see the exact structure I have over here, right? And so, and then I'm going to call this, then you have write. And yeah, similar structure. You could just go ahead and, you know, copy paste this stuff for that, right? And we know that self.data is the current one, right? So this one needs to be the right pointer. Does anyone want to guess how the output would look like for this string which I've written? Okay. 1 second. I can't see the chat. Is there anything on the chat?
Sorry, could you repeat that?
No, I couldn't see the chat. No problem. It's okay.
Oh, okay.
So now let's just go ahead and define this, okay? So if I have defined left as node of 5, right? I've initialized that node of 5. How will the right look like? Okay. So essentially the right would be the 15, right? So this is my left, this is my right. This is essentially my root. Now what I'm going to do here is I'm going to define the root. And for the root, I'll initialize this as. So you have the data, which is your first parameter, right? Which is 10 in our case over here, right? And then I need to pass the left subtree. And then I need to pass the right subtree, right? Now I've defined all this, but how do I look at the information, right? So let's just try printing stuff out, right? So let's print root. So if you see, what it's showing essentially is the information I have over here, right? So this was my left child, this was my root's data, and this was the right child, right? Now let's just try printing it for maybe the left child and the right child, right? So let's just try printing that out. So if you see, in this case, there were no, this node is a leaf node. It did not have any children. That's why the left pointer and the right pointers are not. Yeah. Anyways. Now, are there any questions so far? If not, I'll go to the next part. All right. Awesome. So over here, we're talking about in-order traversal, right? So a very easy way of remembering things, right? When is it in order? When is it pre-order? And when is it post-order? Everything is dependent on the position of your root. Okay. So what do I mean by everything is dependent on the position of the root, right? Let me just give you an example. So basically, if you look at it, in order means it's left, root, and right. This is in order because you always see the left subchild first. You see the left subtree first, then you look at the root, and then you look at the right right subtree, right? Now, basically here the root position is in the middle, which is in order, right? Which is in the order how you see it in the tree, right? Root is always in the middle. Now, what is pre-order, right? Where is the root positioned in pre-order? This was in order. Anyone? Sharmeen has mentioned that, but will anyone want to write their answers there on the chat, right? How does pre-order look like? Okay. So essentially, pre-order says that you need to visit the root first, and then the left, and then the right. Okay. So basically, my root moves to the beginning of this. So essentially, if I have to read the tree, I start from the left node always. But since I moved the root before that, it's called pre-order. Now, similarly, if I had to and then root in the end, right? Over here. So you visit the root in the end. A minute. I don't know where it is. Right? Yeah, my bad. Okay. So this is pre and this is post. So if you guys have any difficulty in remembering what is in order, pre-order, and post-order, just try to visualize a tree in your head and try to read it from left to right. And based on the position of the root, everything decide wherever the root is, that is the position of the root decides the name of the traversal. So if it's in the middle, basically how you read it, it's in order. If it is before the left subtree, it is pre-order. If it is after the right subtree, it is post-order. So I hope everyone got this. A lot of people kind of struggle with remembering what is what traversal, right? So let's just start. So basically, you could do this two ways. You could do it recursively, and you could do it iteratively as well. So over here, I'm going to discuss the recursive solution first for the in-order traversal. What it says is, first you visit the left subtree, and then you visit the root, and then you visit the right subtree, and you keep recursing over it, right? So if a left subtree has a left and right child, you will visit the left child of the left subtree first. Then you would go to the root of that left subtree, and then you would visit the right subtree. Is there any issue with questions?
No, I think you're good.
Okay, cool. All right. So over here, again, we are kind of defining, the tree node. Over here, you can just say def. Again, we're initializing the constructor. And you have self, which is the instance. And what you could do is you could just define the value here. Okay. Now in this value, what I'm going to do is I'm going to say self dot value is equal to 1, and self dot is equal to none. So you could either initialize it in here while as a default parameter, or you could even initialize it inside the constructor, the function. So far, any questions? Right. So basically, this, I can do one thing is I can move this part to the next part. So run that side. Right. And yeah. Now, what are we doing here? Right. Like I mentioned here, you got to visit the left subtree first. Okay. So this is in order, right? Good. So let's initialize a result variable. Okay. And let's initialize a current variable. And here I'm doing this, right? This is basically unpacking the values. The result is an empty array and current is assigned to the root. Now, the next thing what you want to do is, since it's a recursive function, right, I'll be recursing over the current pointer, which is essentially the root in our case. It's a copy of the root. Now, if I say if current dot left, right, is none. What am I doing over here? I'm saying if the value is none, right? Basically, I've hit the leaf node. So let me just give you an example. So you remember this example, right? 5, 10, 15, right? So what essentially happens is I'm starting at this root node. Now I go to the left child of this root node, right? But this left child of this node does not have any other children, right? So basically it's a leaf node, right? So basically I need to print this out. So I will just append the value to the result. So basically post order. So this is going to be added to the result set. Now going back, once I've done printing this, I go back here and then I kind of figure out, hey, what is my right child for this node, right? Which is 15, right? But since this is in order, when I visit the root, I'm going to print the root value as well, right? So, and here when I reach when I reach 15, again, I see if whether it has any children. It does not, it's a leaf node again. So I can just directly print it. So the Inorder traversal for this will look like this. For that tree is going to look like this, right? So basically I'm saying if it is none, add the value, which is result dot append, so current of value, right? Now, what do you do after that? You go to the right child. Okay. Now, what if, this is not none, right? Basically, this is saying that there was no left child in the tree in this example, right? There's no left child in the tree. So I can directly just print the root, the value of the root, which is 1, and just print the right child. Then iterate over the right child, right? Move the pointer to the right child. Now, if there was a left subtree, what you would do is you would store the current node, which is root's left child, right? And now again, you're kind of iterating over this while node dot right. And what I'm trying to do over here is I'm essentially trying to look at the right subtree right now and see if it is equal to the if it's same as the current pointer. Basically this cannot be the it cannot be same as the current pointer because I'm essentially iterating over the left child right now, right? So node dot right not equal to current. Now what I do over here is I'm going to update the value of the node to the right child, and again over here I'm checking if my node dot right is none, right? Or I can just say is none. Then what I do is my node dot right becomes the current, and the current is equal to the left. Okay. I know I'm going a little fast over here. I'm hoping I can help you guys understand while tracing it, right? Because it might be very difficult to, you know, understand it at once altogether. So let me just finish doing this, and then maybe we could try tracing out an example and understand what exactly is happening over here, right? So now what I've done here, right? I'm iterating over the left subtree, right? When I'm inside the left subtree, I'm checking if my node right is not null and the value is not equal to the current, right? I'm going to update the node pointer and make it point to the right subtree. Sorry. Okay. And if my right subtree is empty, right? Basically, it does not have any right subtree. What I'm going to do is I'm going to update my right subtree node dot right pointer to current, which was the root node for this, right? And yeah, excuse me. Just one sec. Sorry about that. I'll stop presenting my video because my internet's a little weak today, right? So I'll just be presenting my screen. Is that fine? Okay, cool. Thank you guys. So basically over here, I'm going to append the current value. So over here, let me just, so now I'm pointing the right subtree to the none object. And now I'm going to update the current pointer, which is going to point to the right subtree, which is current dot right. And then I'm just going to return the result. Okay. Yeah, so, all right. Yeah. Okay. So now, yeah. Yeah. All right. Now, let's just try tracing this, right, for this particular example. So, what is going to happen, right? First time, my root is going to point to 1, right? So far, everyone's good. Any questions? So I'll just trace the code snippet and we'll see if it works, right? Now, let's say for the first time, my root is pointing to 1, right? That's my root. Now, my current is actually equal to the root. So current is equal to root, which is basically 1 in this case, right? Now, the scenario where your current dot left is none is here. So basically, since root dot left is basically a none child, right? What's going to happen? Result is going to be current, right? Which is 1. The value of the current pointer, which is 1. So now my result will have basically 1 in it, right? Now, what am I doing in the next step? Now, what I'm telling my current pointer to be, right? I'm saying over here, I'm updating the current pointer to the right side. Because in Inorder, if I don't have anything on the left, I just need to print the root and the right subtree, right? Did everyone get this so far? Could I get a thumbs up? I know I went a little fast over here because I wanted to basically iterate over it and tell you how it works. Awesome. Cool. So now I'm actually updating my current value to the right subtree. So basically, it's pointing to 2 right now, right? Basically, the node object, which points to 2, which is data is 2. Your left is none. Your left is 3 in our case, and your right is none. Basically, it's pointing to this object now. So far, are we good? Awesome. Now, I'm done with this, right? I'm done with this if condition. It's run. What happens? I go back to my for while loop, right? Now, in my while loop, again, I enter this if condition. In this scenario, this is false because you do have a left child in this case, right? I do have a left child. Basically, my left child is not none. So what am I doing? Now, I essentially, what I'm doing over here is I'm going to create a new pointer or an object, right? Which is pointing to the left subtree, which is basically nothing but a node object, okay? Current. Current will essentially point to a node object whose data is 3, right? But your left and right are none, right? Because this is a leaf node. Did everyone get this? Okay, cool. Now, I've done this, right? Now, what do I look at it next? I'm saying if my node, while my node of, right is not none and it's not equal to current. So basically this condition is kind of false now. This while loop will not run, right? So what do you think should happen next? If your while loop is not running, what should happen? So this while loop is not running. Now the inner while is not running now. What's going to happen is it's going to go back to the outer while. It's going to check if the left subtree of this particular node, which is your current right now, is none, which it is. It's going to kind of add that result. Huh. Okay. 1 minute. Give me a second. I might have made a mistake, but let me just check it. Right. So I'm saying tree of node, which is going to be my root. Now I'm saying there's a right child, which is root dot right, which is going to be like tree of node, which is 2. And then I have a root dot right dot left. Yeah, sure, I'll do that. C1. So the result outside is going to be solution, which is my class. In that I have this function called Inorder Traversal. And I'm just going to say root. Now let's see if I've So basically, this part needs to move out. Yeah. So essentially the mistake I made was the indentation over here. That side was not making sense. So anyways, so over here what's happening is, since the right child is none, is going to assign the current to the left child, which is also kind of null. So what essentially it's doing, it's just getting the value over here and printing that out. So yeah. Any questions so far? If you haven't understood it, I could go over it again. So essentially, the basic principle is you have to keep iterating over the left subtree in a recursive fashion and keep going till you traverse all the, till you hit the leaf nodes, basically. Your exit condition for your recursion is going to be your leaf nodes. And what you want to do next is, once you've traversed all the leaf nodes for the left subtree, you're going to come back to the root and print the root. And after that, you're going to recursively go over the right subtree in the same fashion, right? So you'll always traverse the left subchild first and right subchild first. What essentially I could do is I could skim over I'll just move to the BST section of it, right? So that you get an idea of it. These problem statements are already there since we are kind of running short on time, and the solutions have already are already there for this, and you can use them and decode as well. I have put in some iterative solutions as well as the recursive solutions, but I'll just go to the BST section right now so that I can cover more ground. All right. If you guys want, I could add in some more notes regarding the trace backing of that to the solution notebook, since we are kind of skimming through stuff. Okay. And I think my net's back, so let's just get started. Okay, so now let's talk about the binary search tree, right? So if everyone remembers what Sherman said. So in a binary search tree, you first define the root node, and everything else, the placement of every other node depends on your root node. And you always check if you compared everything with the root node first. If it's lesser than the root node, it will be in the left subtree always. If it's greater than the root node, it's going to be in the right subtree. You will not have duplicates in this case, right? Which is different compared to your normal binary trees. You could have duplicates there, but in terms of binary search trees, you cannot have duplicates, right? So this is how the kind of template class looks like for the binary search tree right now. Let's just start over here, what we are doing in the binary search tree. Yeah, okay. So basically I've initialized the root node over here, and we'll be using the same node class which we had defined early on, right? So for insertion, the rules are pretty much the same, right? In insertion, I'm checking if my value which I'm trying to add is greater than my root. So the first condition would look like if the value, which is what you're trying to add, is lesser than the root node, right? Because I want to look at this left subtree first. It's just a preference, but it can be anything if you guys like, right? Now what I do is, if it's less than the root, I'm going to look at root.left. Basically, root.left is telling me if there is anything there in the left subtree already or not, right? Initially, you won't have anything in the left subtree. If I have to take this example, right? So initially, when I just define the root node, there's going to be nothing. It won't have a left child, it won't have a right child. So if it is none, what I'm going to do is I'm just going to put root.left dot value is going to be a node, right? With the value. Basically, I'm adding, so how it's going to look like now is, initially I just had 10, right? I had 10. So no left child, no right child. Now I have 10 and I also have a left child being added to it, right? Which is your 5 in this case. Is that clear for everyone? Why I'm doing this over here? So basically it was kind of an empty tree, right? Awesome, cool. Now, what if it's not an empty tree? What do I do, right? If it has some values. So if it has some values, what you do is you recursively call the same function, which is self.insert. Because again, I need to iterate over the whole left subtree to find where I need to place this, right? So that's why there's a recursion happening. Say value. So if a value is lesser than the root, I need to keep checking at what point in my left subtree will I add this value, right? It could be here, it could be a couple of levels below that as well, based on the number. Let's say if I had put -1, right? So first it would go to 10, then it would go to 5. Then if I've added 5, and then it sees, oh, this has a left, it has another left child, right? So again, it's going to look at this left subtree, and this value is 1, right? So if I have to add -1 or 0, I essentially need to add it to the left child of this 1, which is currently a leaf node, right? Similarly, what do I do if my value is greater than your root node? So as a practice, usually my preference is putting in the exact condition rather than leaving, things a little ambiguous in nature. It's a good, helpful thing to do when you're especially coding stuff out in production, right? It's really good. Always go with strict conditions, whether you're testing stuff or whether you're writing code. It will reduce a lot of errors and it will help you trace back a lot of things. Because let's say if I did not put this condition, right? And there was another scenario, everything would fall into that else bucket and things might go wrong. So that's something you can always do, right? So this is an elif. Now, or I could just say an else, right? What I could do is inside that, maybe inside the else, I could put the conditions. Anyway, whichever you guys prefer, right? So if say root dot right, again, I'm checking if you have a right subtree, right? So again, if it is null, right? If you know the value is greater. Now I can just go back, put this in so that it's similar to whatever conditions I've mentioned before. So I'm saying if the value is greater than the root data, then I'm checking if there is an already, if a right subtree exists or not, which it doesn't. So what's the thing, what's it going to look like? It's going to look like root.right. So basically I'm going to assign a new node to the child, to the right child, right? Which is what we were doing here, right? So right.value is going to be node of val. Now, what if a right subtree exists? Can anyone guess what the X statement is going to look like? Okay, since we're kind of running short on time, I'm just going to put it out there. So it's going to be self.insert, right? But what am I going to insert? I'm going to look at the root node, which I need to put here as well. My bad. Because I'm looking at the instance root and dot right. I'm saying root and value, right? Now, what is this doing? This is just for the initialization purpose, right? So I'm just saying self.root is none. Initialize this to the initialize that value as the root node, right? Now, if this is not the case, right? If I have already defined the root node, you can call the insert function. You can call the self, you can call the insert function. The insert function would be called on the instance root value and right. Did everyone follow this? So let's try and code this example, okay? Right. So basically, I would create an instance of an object of this class binary search tree, which is going to be T. Okay. Now what I'm going to do? How will I add the root node? Right. So basically, I'm going to do 10 dot add. So now, if I have to print this, right? How will I print this? I'm just going to say print T dot root, which tells you this node. Now, let's say I want to add another element, which is say 5. Oops. Oh, none type has no value. Okay. See where that's happening. If root is not one, you do this. This root is back. Okay. My root of data is this and this. This is none. I'm adding this value. My bad. So basically, if it's a none object, it cannot have anything, right? So I have to initialize it. All right. So I'll reinstantiate this and awesome. So now if I print this, you see the values have changed. Now I have a left subtree and the right subtree, right? Now if I have to add values, I have to, let's add 15 and 1. And let's also try adding the -1 scenario, which I was telling you, right? So this 15, we know that 1, 5 I look at this, I have this. Now if I have to look at the value below that, I need to look at sort left, which gives me 1 and 5, right? And if I have to look at the right subtree, you say top right. Now, let's say I want to add -1. Where do you think it's gonna go? Recursion depth exceeded. Okay. Over here, I try to add a duplicate value. Nothing essentially changed, right? Because like I mentioned before, binary search tree does not allow you to basically add duplicate values. So this is how you pretty much create a binary search tree, right? What we need to do next is you need to write a search function for this, right? Rishika, do we have time or should I just go over the high level logic?
Yeah, we have just a few minutes left, so maybe go over it more like in high level.
Yeah,
if that's okay. Yeah.
Yeah. Awesome. So basically, the searching is also very similar to the insertion behavior, right? You could think of it very similar to the binary search, where you divide your array into 2 halves, and you try to search in one half or the second half, right? Based on the value, because you usually do binary search on a sorted array, right? In this case, if I look at the binary search tree, essentially this is sorted, right? So if I have to like print this out in like a sorted manner, how would I do it, right? I would essentially look at the Inorder Traversal of this, right? Which would be like this, for this example, if I just consider the 1, 2, 3 tree, right? It's going to be 1. Just look at the subtree, which is 1, 2, 3. If I have to get the sorted keys, I can just print the Inorder Traversal of this binary search tree, right? Which is 1, 2, and 3. Now, if I have to look at the okay, yeah. So now, how do I search? It's very simple. So it's very similar to the binary search you do on arrays, right? You take the value, you compare it with the middle element in the array, but over here, the root is acting like the middle element, right? So first, let's say if I want to search 21 in this GIF. So since I found it at the root node, I can directly return saying that, hey, I found the key, right? But let's say if I have to search for something, say 14, right? Which is not found in the root node. But when I look, but I know it is lesser than 21. So I look at the left subtree. When I went to the left subtree, the first child which I encountered essentially had the value 14. So I can directly return that, right? Let's say if I have to search for another value, which is say, let's see, 32, right? Now I know 32 is greater than 21, right? And then I come to this, it's 28 right now, right? 28 is, I know 32 is greater than 28. And so I'm going to look at the right child of 28. So I'm going root, right, right. And in the other case, I was going root, left, right? So basically, where you're checking at any given point of time, whether a value is greater than the root of your tree. If it's greater than the root of your tree, you go to the right subtree. If it's lesser than the root of your tree, you go to the left subtree. When you arrive at the left subtree, again you check if the root of the left subtree is greater than or equal to the value you're trying to search. Based on that, you're going to either traverse the left subtree of that tree or the right subtree. So yeah, essentially that is the very high level logic. Very kind of similar to how the insertion happens. If you guys have any questions, sorry, we didn't have time to cover a lot of things, but I have the solutions and these problems in the notebook. So you could always reach out to me on Slack if you have any further queries. I'd be happy to help you guys out. So if you guys have any questions, I can take them right now. Yeah.
I don't see any questions in the chat or the Q&A currently.
All right, then I think we can wrap it up then, because I won't be able to cover the coding for sure.
Yeah. No worries. Yeah.
All right. Thank you.
All right. Let me pull this up. All right, so just to wrap this up, our next session will be in 2 weeks. Same time, same day, Thursday, 8 p.m. Eastern. That'll be session number 7. So please do join us. It's gonna be the same exact Zoom link that we've been using. And if you have any further questions beyond today's session or about previous sessions, join our Slack community. The link has been shared throughout today's session, and we have a Slack channel dedicated for this series. Is this right here? So please do join that as well. And that is it. Thank you so much, everyone, for joining. Thank you to Charmaine and Shivangi for a wonderful session. And we hope to see all of you in a couple weeks. Thank you. Bye-bye.